Starting out using the calculator to find sine of 2, tangent of pi over 5, and secant of 1.3, what you need to know is that I have other classes, and so my calculators will often be set to degrees mode. Not only that, but sometimes my calculators are not set to the correct number of digits that are necessary for an AP exam. So would you take your calculator, open it up, go to settings and status on your doc page, document settings. What I like is fix 4. You have to display 3 decimal places of accuracy. You do not have to round. So I like to display for myself 4 decimal places of accuracy just so I can see it. And then I say, okay. And up there between radians and degrees, you feel free to swap as necessary. For this problem right here, sine of 2, he wants it in degrees. In radians. So I'm going to hit the trig button. I'm going to hit the sine button. I'm going to hit 2. And then I hit enter. And what happened? Oh yeah, don't forget to hit control and then enter. And now I have my decimals, okay? So that is going to be what? 0.909 equals 0.909. And then a tangent, I'm supposed to do negative pi over 5. So I've got my trig button here. I've got tangent. I've got my negative. And I am a cheater, so I just use PI because I can type. You guys can find the pi symbol right there, okay? But I like to cheat. Sorry. Now, pi over 5, hit control and then enter. I don't know what that number's going to be. That's not one that I would normally have memorized. 0.726, negative 0.726, okay? And then secant of 1.3 would be right here. Secant of 1.3. Again, control enter. And boom, you have 3.738. 3.738. Now, just a word to the wise, whenever you're doing sine or cosine, your number should be between 1 and negative 1. Okay, that's just unless there's a multiplier in front, which we'll take a look at that in a minute. Now that we've done that, we also want to remember how to do basic trigonometry from Math 2 or from, when you were first introduced to trig. This little notation right here, I find it unusual. I've never really seen it look like that before, but what he means is 0.5 in radians. He said he wanted you to be in radians, so don't think that that's degrees, okay? And we do want to use SOHCAHTOA. And our job, as always, is to determine which function to use, sine, cosine, or tangent. And how are we determining that? Well, if they give us an opposite and a hypotenuse, or an adjacent and a hypotenuse, or an opposite and adjacent, then we know. And taking a look at this problem, what I see is that from this angle, that side is an opposite side. And this side looks like the hypotenuse, and so I'm going to assume that they're drawing it correctly. And this side would be the adjacent side, which is not a side that I know anything about or that I care about. So OH means I'm in the land of sine, and I want to say that sine of 0.5 equals 5 opposite over hypotenuse, 5 over x. Now, just a word about cross multiplying. Yeah. You have A over B equals C over D. And when you cross multiply, you get A times D equals B times C. Cool. What if I wanted to solve for D specifically? Okay, if I wanted to solve for D specifically, that means I'm going to divide by A. I'm going to divide by A. And what it means is that if I have some, heart over here, and I have some kind of square over here, and I have some kind of triangle over here, and this is just one, watch this. What I'm trying to let you know is that this is A, this is C, and this is, what is this one? What is this one? This one is D. I eventually want to be able to say that triangle equals, ready? C doesn't move. A is the thing that moved. Okay, so think about it like this. C doesn't move. It will stay on top. A will be in the denominator, and D is the thing that I'm solving for. This is just one of those, if you can kind of memorize this quick trick that it'll be C over A, then you don't have to do so much work with your cross multiplying. Now, if all of this did not make any sense to you, don't use it. Just follow the process for, cross multiplying. Mentioned to you, again, cross multiply to solve, but I know the shortcut. My shortcut will be that x equals 5 over sine of 0.5. And I can put that into my calculator. Let's see, I want a calculator page. Thank you very much. Not you. Calculator page. I want it to be sine 5 divided by sine of 0.5 in radians, and control and shift. And what do I get? My answer is that x equals 10.429. 429. And if you did not get as many decimal places than me, then double check your settings on your document. And just take a quick moment. A half of a radian. Yeah, I don't know. It's kind of hard to make sense of, but it looks like it's longer than this leg anyway. This leg was a distance of 5, so the hypotenuse is clearly longer. That's just a little quick, did I do it right kind of thing. Over here, okay, so this was straightforward. I was looking for the length of the side. When looking for the length of a side, we will use our trig ratios to find it by solving for x. But when we are looking for an angle, you have to remember what your math teacher taught you before, which is what? Inverse trig is for finding an angle. Sorry about my handwriting up there. Let's just move past it. I'm saying that this is the opposite side, and this is the adjacent side, and this right here is the hypotenuse, and I don't know anything about it, and I don't care. It's not helping me in any way to have any information about the hypotenuse, so it's not sine, it's not cosine. I'm squarely in the territory of tangent, so I say that tangent of that angle, right, my given angle, they're calling it theta, is going to be opposite over adjacent, which is 2 over 5. How do I use an inverse? You swap where x and y live, and you turn it into the inverse function so that the calculator knows that it's finding an inverse. So what you will want to look for is the inverse tan function on your calculator, and you are going to plug in 2 over 5 as the input to that function, okay? Because remember, you're swapping x and y. So now I have trig, and where is my inverse? Right there. And I say that this is 2 divided by 5, and I hit control and I hit enter, and that's my answer in radians, okay? And it's like, it's kind of feels not good. I'm not happy about that answer. 0.3805. 380 is good enough for me. So I just got to take a moment and kind of just throw it into degrees just so I could think about it for a second. Hit control, hit enter. Look at that. 21 degrees is what gives me that. And I'm saying that this is a very short side. So sure, 21 degrees sort of makes sense to me. Now, just, so I could prove that I'm doing it correctly because, these answers were hard. Let's double check the answer key. So where is the answer key? Boom. This guy up here is the answer key. I definitely got the right answer for all of those problems, and we get to move on. Also, I will mention that the answer key, very interestingly enough, has these things where they were being graphed on the coordinate plane, and it looks like since he made this answer key, he decided to just separate them out into different actual graphs. So if you have access to the answer key to the example problems, don't let it confuse you. I'm going to go ahead and graph them all. See this? All individually. Now, this is all very important stuff about trig that you want to remember, and so I would say pause and read it. Now that you've read that, I would love for you to just have some sine and cosine graphs memorized. From heart, you can always create sine and cosine. The other ones, I won't lie, I don't really have them memorized. I can come up with them when necessary. And if I'm in the middle of teaching this course, then I do kind of have it memorized. But like in general, do I have them memorized? No. However, I can graph sine in my sleep. Ready? I start up here. I go to here. I go down to there. I go up to here. And then I go back up to here. Nope. Sorry. That's cosine. So I start here. I go there. I go here. I go there. I go there. Ready? Boom. That's sine. Cosine. What does cosine look like? I start up here, I go down there, I go down there, I come up here, and then I come up here. And it's curvy. Like they're the tops and bottoms of some circles. So they're not straight. That's not a V shape. Now that I've done that, I could probably reproduce it again for another period. This one's kind of harder. There we go. Something like that. And now I'm good. When I think about trig functions, I think of sine, then I think of cosine, then I think of tangent. I always do it that way because when I memorize things about those functions, that's the order that I memorize them in. Ready? Sine, cosine, then tangent. Then I memorize cosecant and secant and cotangent. And the reason that I did that is because cosecant is 1 over sine and secant is 1 over cosine and cotangent is 1 over tangent. And so that's why I have them memorized in that order, which is my excuse for why I'm doing tangent first. So I wanted to make you guys like a little table of sine values and cosine values because I know that tangent has some asymptotes in it. And specifically, where will tangent have some asymptotes? Well, there is another definition of cotangent and of tangent, which I'm about to remind you of, which is that this is sine over cosine, and that this guy is cosine over sine. I don't know if I'm going to get to this one or not, but I'm definitely going to use this. Anytime I'm dividing by 0, I will get undefined, which means that there is an asymptote there. So if I am looking at everywhere that cosine, ready, was equal to 0, here, 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 I'm expecting that tangent will have the same thing going on. Now, to make this a little bit easier for you to visualize, I did go snag this beautiful table from Math for Blondes, which is kind of a funny webpage. But this graph is accurate. I don't really need this. I don't really need this. I don't really need this. But I'm very focused on pi over 2, pi, 3 pi over 2, and 2 pi, because these are the moments of time that are marked on my graph that I am assuming there's going to be some asymptotes. And so I'm just double checking here. Can we look at tangent? This guy, it's a foreign website, so they're not using the notation you would think. Tangent right here is undefined where? At pi over 2. Can I highlight that? Yeah, pi over 2 and 3 pi over 2. So pi over 2 and 3 pi over 2. Well, 3 pi over 2 is over here, right? They didn't get that far. We just got to pi. But I do want to mention to you that I know that this thing has a period of pi, right? Because, boom, he said so. And so that means that here's my positive pi over 2, here's my negative pi over 2. That distance altogether, take a pi over 2, add another pi over 2, you get a whole pi. So I'm feeling good about having found, ready, all the places where cosine is going to be dividing my function. And I wish he had graphed this a little bit differently, because this is pi over 2 and this is negative pi over 2. And it doesn't quite line up. You see how he left room here for pi over 4? I don't really care about that. Ready? I know the graph goes like this, and I know that the graph goes like that. And then I know that the graph goes like this, and the graph goes like that. I just have those shapes memorized, and I recommend that you memorize those shapes too if you are keeping tangent in your brain. What do you mean, Ms. Chatra? Do I have to keep tangent in my brain? Only if you want to get a 5 on the AP exam. Not everybody wants to get a 5. Not everybody can keep this stuff kind of memorized in their heads. Is it possible to get a 5 without having that memorized? Yes. It is. It is totally possible to get away with not having that memorized. Now that I've said that, though, let's just go ahead and do cosecant and cosecant and secant really quickly. Again, I'm using this factoid right here, which is that cosecant is 1 over sine. So where is sine equal to 0? It's equal to 0 here and here. And so that means that there will be an asymptote right here, and there will also be another asymptote right here, and that means that there's another asymptote right here, and there's also another one right here, and then there's right here, because cosecant and secant do not have the same period. Okay, what they have is, oh wait, do they? Each of these last two functions has a period of pi, but doesn't cosecant also have a period of pi? Doesn't cosecant also have a period of pi? This is cosecant. Yeah. Okay, so we're good. Again, I wish he'd graph these a little bit differently because it makes it feel like he let this one go to 2 pi, he let this one go to 2 pi, but he only let this one go to pi. So it doesn't this graph is stretched out. This graph has been scrunched in. You see, so if you're feeling like these are a little bit awkward, graph them on a regular piece of paper where you are making them be the same distance apart, and I think it will help. When am I equal to 0? Oh, yeah. So what's the shape of cosecant then? This first guy, ready? It goes up like this. This other guy, it goes down like that. And then this guy goes down like that. And this guy goes up like that. And how did I know that? Again, I have that bit about cosecant memorized. Where the asymptotes are, that's the part I can't really keep in my mind. Mentioning to you that on this cosecant graph right here, cosecant graph. Oh, my bad. This is cosecant. It says it's at 1. I am at 1. And this is, by the way, pi over 2, just like it said it would be. Pi over 2, I'm at a height of 1. And right here, I'm at a height of -1 at 3 pi over 2. So there you go. Now, secant is defined as the 1 over cosine, which means that everywhere that cosine is 0, I will have an asymptote. And I've already highlighted all those spots. Ready? Pi over 2 and 3 pi over 2 and negative pi over 2 and negative 3 pi over 2. And let's double check that right here because I'm having a moment where I'm not remembering this. 0, it's at 1. Okay, so we're going to start right here. We're going to go like this. We're going to go like this. We're going to go like this. And we're going to go like that. And we are going to go like this. Oops, my bad. Wow, I didn't know it could do that. That was cool. It's like I had a little circle just to pop up there. And then here, and then here. Now, what about cotangent? Cotangent is like a flipping of tangent. Remember, we do it's the reciprocal of tangent. So let's just double check again where my asymptotes are. Clean this up. This guy right here, this guy is cotangent. That one was tangent. This one is cotangent. It is undefined right here. Oh, here, we do any yellow? Boom. It is undefined right here. It is undefined again at pi. And it is undefined again at 2 pi, which is all the way out here, which he didn't graph for us. I'm going to be mad about that for a while. Okay, so then we will do it like this. Notice that it is at a height of 1 for pi over 4. So this is pi over 4, and it is at a height of 1, which means that it goes like this. Ready? It's like a flipping of tangent on its axis. Imagine that I was doing that shape. Okay, so that's the shape that I'm trying to draw. And I know my graphs aren't pretty, and your graphs might not be pretty either. And guess what? You don't have to graph anything on the AP Calc exam. That's not a requirement. What you need to be able to do is pull values out of a graph to quickly give yourself an answer to a trig question like, what is cotangent of 0? Well, cotangent of 0, we just saw right here, is undefined. If you have the graph memorized, you know that it's undefined there. Okay? Now, again, really important, beautiful stuff here, telling you how to find the period of various types of functions, telling you what this thing, gives you in terms of the shape of the graph, what kind of shifting is going on, left, right, up, down, all this stuff. Pause it, read it. So now we are trying to graph this then, using that information. This -5, remember how I mentioned a multiplier earlier? It is a multiplier. What it does is it takes this beautiful graph of cosine, which I snagged from above and I already had copied and pasted to right here. What it does is it flips it. First of all, it flips it because it's negative, and it makes it grow faster too. That's called amplitude, right? So my amplitude is going to go up to 5, and it's going to go down to -5. And if it was not negative, it would go like that. But since it is actually negative, it instead goes like this. Boom. Oh, you know, this is hard to draw because this is pi right here. And I'm going to call it quits there. X over 2 is going to, ready? X over 2 is going to be this little modifier right here, B. And it says that changes the period. So the period is going to be 2 pi over the absolute value of B, which is 1/2. What do you do with this? Well, you take 2 pi and you divide it by the absolute value of a half, which is a half, which means that I have 2 pi times 2 over 1, which means that I have 4 pi. So instead of having a period of 2 pi, which is what cosine normally has, I will now have a period of 4 pi. So it means I'm supposed to take this shape and I'm supposed to stretch it out. Let me just show you the factoring part, because this is the kind of thing that you would go over in a very comprehensive pre-calc class. Sine of 2, well, hold on. Let me just do it like this. 2t minus pi over 2. Imagine that I put this into a set of boxes. I don't know what that 20 is doing right there. And I said to myself, I'm going to factor out a 2. Well, what's left up here is a t, but what's left up here? Well, it's not a 20. I think that's the page number. What this is if I take 2 and I multiply something by 2, what I get is negative pi over 2. It must have been, ready, negative pi over 4. Because let's look at this. Pi over 4 times 2 is the same thing as 2 pi over 4, which is the same thing as 1/2 pi. Okay, so I had that. And let's make it negative for good measure. Okay, so that's what I did, is I factored this, and my new function is sine of 2 and t minus pi over 4. Why did I do this? Well, first of all, I'm going to let you know that this I now know is going to change. Let's see, what does it say? It says that this number is going to change. B is going to change my period, and C is going to change my horizontal shift. And so my period was going to be 2 pi over the absolute value of B, and B is 2. And so that's just what? Pi. So now I have a period of pi, and I know this is a horizontal shift of negative C, which means this is a horizontal shift of negative pi, which negative pi over 4 means that I'm moving right. Pi over 4. Okay, so then I'm taking a look at how to actually graph this, and I'm saying, well, notice here, this is pi, so 1, 2, 3, 4 marks, 1, 2, 3, 4 marks. This would be 2 pi. And normally, sine goes like that. Only in this case, I know that the period is pi. So instead, it goes like that. And because I have this negative pi over 4 business, meaning that it shifted right, I'm going to take this, I'm going to pick it up, and I'm just going to move it over to there. And that's where it lives now. And so that's your graph. If you want to make your graph big enough, you got to repeat this twice, right? Is it this one? And keep going. So there you go. Now, the next problem here is about Pythagorean theorem, the Pythagorean identity, this guy. If you ask me nicely, I'll make you a freestyle on what Pythagorean identity, this particular Pythagorean identity is. If you're already familiar with identities, you can skip it. So look for a freestyle if you want to know more. Now, I'm also going to have to use my own advice, which is that there's not really enough room for me to do this problem right there. So I'm trying to put it someplace where I have plenty of room to write. And now I have it. So when I work with the Pythagorean identity, this guy, I'm familiar with kind of manipulating it around. For example, I am eyeballing this guy. I see a cosine. Here I see a sine squared theta. I want to replace this sine squared theta with that sine squared theta. So I'm going to, step 1, solve for sine squared theta in this Pythagorean identity. So sine squared theta plus cosine squared theta equals 1. I'm going to minus cosine squared theta minus cosine squared theta. And that gives me sine squared theta is equal to 1 minus cosine squared theta. I understand that that's an ugly theta. Okay, so now that I have that substitution, I can come in here and actually make the substitution. So step 2, make the substitution. And the substitution would be that 2 cosine of theta minus sine squared of theta equals -2 is going to be replaced. So what is it going to be replaced with? This is moving in right here. And so, do you want another color? Should we pick a purple? How about that? 1 minus cosine squared theta. And I'm seeing if there's anything that can be done here. Yeah, there's a negative sign, so I can distribute. And I have 2 cosine of theta minus 1 plus cosine squared theta equals -2. And what else can be done? Well, I can add 2 to both sides. And not only that, but I recognize this. This is the first time you're seeing it, so you probably don't recognize it. But this is actually a quadratic. I'll show you why and how. I'm going to say that I have cosine squared theta, and then I have this 2 cosine of theta, and then right here, 2 minus 1 is plus 1, and that equals 0. And now I'm going to make another substitution. You don't have to make a substitution when you start to be able to recognize this problem. But because you don't recognize this problem, I'm going to make the substitution for you, okay? How about I pick this black, and I will say that x equals cosine of theta, which means right here I have x squared, and right there I have 2x, and right here I have plus 1, and that equals 0. See the substitution? This is step 3, is to substitute this to make sense of the quadratic. And here's my quadratic. Ready? X factor for me, please. X squared plus 2x plus 1. If you're my student, you know how to do this because you've taken this verbal quiz twice. Take the square root in purple. Square root. That means I have x plus 1 equals 0 and minus 1. X equals -1. But remember that x was cosine. So we are going to substitute back. Step 4. Step 4 was up here. Step 4 was to factor and solve. And here, step 5 is to substitute back. So I now have cosine of theta equals -1. And step 6 is to make sense of the problem. As far as the solution goes, I can make a quick little graph of cosine and there. Nope, that's not that sign. This is 2 pi. This is pi. And that's where it's equal to -1. So cosine of theta equals -1 when theta is equal to pi. And specifically in the interval. So now let me read the problem because I'm not sure that I've done that yet. Use the Pythagorean identity to rewrite this crazy looking thing in a form which only contains one trig function. That was him giving you a hint that you needed to solve for sine squared theta and do this substitution right here. That was very nice of him to give you that hint. Then, without using a calculator, solve for theta on that interval. And the interval is between 0 and 2 pi. So right here, I got the pi. So now that I think I have an answer that theta is equal to -1 when I have pi, and I believe that's the answer, take a look at what the rest of the problem says. He says, use your calculator to verify your solution, which I find hilarious because I put it into my calculator and this is what I got. Hold on a second. Let me double check and make sure that you know how to put it into the calculator. Ready? So we are doing a solve and we say I just need to be able to see the problem when I'm doing it. Here we go. Solve, we say 2 cosine, sorry, trig button, cosine is right there, and of x, and then I have a minus, and I have a sine. This is why I'm actually showing you these steps, is because a lot of times you guys forget that. Sine, when you want to square it on this calculator, watch this, ready? I am deliberately putting that squared in the wrong place. Can you see why it's in the wrong place? Because it's supposed to be outside these big parentheses. Now, why? Because I did not want to square x. I'm not squaring x. I'm squaring sine. I'm going to figure out what x is. I'm going to take sine of that x, and then I'm going to square it. Okay, so just make sure that you put it in like that. And then that thing equals this -2 and comma and x. And just in case you didn't notice, every button that I press is turning red. So when I did all of this work, if you got lost, you can come back to it, open, rewind, and come back here and see the buttons as I'm pressing them. I hit enter, and like I told you, I got this ugly, nasty thing, which is not much of an answer. Okay, they're like, I don't even understand that answer. Of course not. It's because it's computer programming. That's what this answer is. It's computer programming. And let's see if I can use the computer to kind of pop out the answer that I wanted. Okay, that pi answer. Now, if you look at this, this is supposed to be my solution. Well, this is a variable, and it means that you can kind of look in all of the different places that cosine equals -1. I did a quick little sketch of it, cosine right here. It equals, -1 right here at pi. But then if I keep going at 3 pi, and I keep going to 4 pi, I'll get another period, right? It equals -1 right here at 3 pi as well. So it equaled it at at pi and 3 pi. And shoot, for that matter, over here at -pi. So there's an infinite number of places where this thing is going to equal -1. And so in this moment, oh, I forgot. There's a way to restrict the domain. Oh, we should look at that. But just in case you forget to, I just wanted to show this to you. Right here, 2 times n1 minus 1, put parentheses around that, times pi. What do? First of all, set n to be 0. Why? Because that's what computer programmers do. Then n equals 1. Then n equals 2. Then n equals 3. You're not always going to need all of these, but I just wanted you to be able to see it. 2 times 0, that's what x is. X is 2 times 0, because I'm setting n to be 0, minus a 1. Throw parentheses around all of that, and then multiply that by pi. What's 2 times 0? It's 0. What's 0 minus 1? It's -1. And what's -1 times pi? It is -pi. I literally just told you that that was one of the places. Okay, this answer, not useful, not in my domain. How about this answer? X equals 2 times 1 minus 1 and pi right there. And so 2 minus 1 is 2, minus 1 is 1, and 1 times pi is just 1 pi. And that's the answer that I got. That is the answer that I got, and I believe it's the correct answer. Why would I keep going? I just wanted to show you what it looks like, okay? Are you starting to feel a pattern with the counting here? That was -1. This is +1. What am I going to get over here? 2 times 2 minus 1. And right there, there's pi. 2 times 2 is 4. And 4 minus, 1 is 3. And 3 pi is not in my domain. But I did tell you that it is equal to -1 at 3 pi. I don't need to do this one because it's definitely out of the domain. Out of domain. This was out of domain. And this one also obviously will be out of domain. All right, I looked it up. This is the solve without domain restriction. This one is with the domain restriction. You guys don't know how to put this in, that one, probably. So let me just take it out. I'll take it out and add it in again. Ready? It's called such that, and you're going to need this character a bunch of times in calculus, so why not introduce it right now? such that it funnels values into something. So the values that I'm funneling in just happen to be the domain. So there's 0, and then in the same place right there is the less than or equal to. And again, I'll remind you that I'm typing stuff over here, so you could see on the left when I hit a button. And so let me make sure you see it again. There is that less than, there's the such that. And this is an obscure piece of knowledge that I don't know that you'll be able to retain. I can do this. I've shown you three different ways now. So, whichever one sticks. Okay, there you go. Boom, and it'll just pop out the exact answer. Oops, that one, though, I was supposed to do what? Wasn't I supposed to just do a less than? Ta-da.